Okay. So we're going to start with just one population proportion, and then we'll move on next time and we'll talk about the difference in two proportions. So today, just one. So suppose a legislature wonders whether more than half of the voters in her district favored a new law that would reduce the legal blood alcohol legal BAC that defines drunk driving. Suppose that P is the proportion of voters in the district who favor the lower limit. Write the null and the alternative. So she wonders whether more than 50%. So I think that's kind of the HA. Does that make sense? So proportion is bigger than half. So more than 50% support lowering the blood alcohol content limit. And then what would H naught be? Mm-hmm. 0.5. That or equal to value is called the null value, or the value that is like the changing point between the two hypotheses. Does that make sense? So in this case, our null value is 0.5. That isn't the only null value that you ever use. You might be testing like, is the proportion of people who are brown-eyed actually 30%, in which case your null value is 0.3. Does that make sense? It might be, or green-eyed is 2%. Probably, that null value is 0.02. So in this case, null value is 0.5, but not always. But the point is, it's the point where you switch from one to the other. It's the null value. And we talked a little bit about one-sided, two-sided, right? Okay. Because the null value really is the important thing, sometimes your H naughts are written without the or equal to things. So you can do it either way. Does that make sense? So it's just kind of implied that it could be this or lower or this or higher in each respective situation. But when you see the first thing, you say H naught is P, a proportion value equals some specific null value versus those two things are not equal. This doesn't specify which direction, and that's called a two-sided test. Both of the other ones specify directions, and those are both one-sided tests. Okay. Next, we're going to talk about how to find z-values. So you operate under the assumption that the null hypothesis is true. So to find the test statistic, which is going to, in this case, for our other stuff, it was a chi-squared value. For this stuff, it's going to be a z-value. And so this will be a z equals, when we get into stuff with means, it's going to be a t-value because of that whole t-distribution business going on. This is your sample statistic minus your null value, and you divide by the standard error of your null value, or standard deviation of your null value. It's kind of like that x minus mu over sigma thing, right? And here is that for proportions. The sample statistic you have is your p hat. The null value is that p naught thing, that's the breaking point in your hypothesis test. And you divide by the standard error actually of p naught this time, as opposed to p hat. Because you're assuming that p naught is the true value, so you find its standard deviation / standard error not of p hat. That's a little bit different, right? Okay. So, but the formula for it is no different than the confidence interval formula for standard error, is it? It's just p naught instead of p hat, right? Okay. And then the z-test statistic is a standardized score that measures how far away from the mean is this thing in terms of standard deviations. It's like once your z gets above like 2.5, that's kind of unlikely. Does that make sense? Once it gets below negative 2.5, also kind of unlikely, right? That's the whole, remember, most stuff is within 3 standard deviations, or you think about your empirical rule. Okay, let's actually find a z statistic. So because this formula is, I'm just going to say z equals p hat minus p naught over standard error of p naught, I'd suggest finding this standard error thing first, and then using the answer in the rest of your calculations. So the standard error of p naught is big ol' square root sign, p naught, 1 minus p naught, over n, right? So we have a sample size of 500. We observe some proportion of the people there, like 30% say were left-handed, and we assumed that in the population 20% is left-handed. Does that seem unlikely that if 20% are actually left-handed, you're going to get a 30% result? In a sample that big, it seems unlikely, right? Okay, so standard error. What goes in for p naught? 0.2, yep. Over 500. So calculator that, because calculator needs a verb. It's much, much fun. Tell me, yeah, I know. Tell me what you get. And leave lots of decimals because that'll make your final answer more accurate. You want to say? Do you get it already?
Yeah. Sorry.
It's okay.
0.017888544.
So 889 then.
Yeah.
Yep. So then the z-score is p hat, which is 0.3, minus 0.2, divided by 0.017889. And then what do you get for that? I got kind of huge-ish.
5.5.
In the world of z-scores, is that big?
Yeah.
Yeah. In the world of z-scores, remember that how many standard deviations away give you almost everybody? 3. So there's 99.7%. So this guy's in the top, like he's way the heck out there, right? Which leads you to believe that you would then probably reject this thing, right? And say, I think that whatever my HA was true instead. Okay, but yeah, that once your number is definitely more than 3, you're certainly rejecting H naught. Okay. So the p-value is computed by assuming that the null hypothesis is true, and then it asks, if this is true, how likely is it that I'm going to see something like this? Is it very likely or not very likely? Where the previous example, that was not very likely. And so for a greater than alternative hypothesis, so something like H naught P is bigger than some P naught, you're finding the probability that your Z, your Z is bigger than or equal to this Z star thing. And what that's saying is, what's the chance I'm either there or above? And this also is a one-sided thing. What about for a less than alternative hypothesis?
Less than that.
And which direction does your Z table go? Less than. It goes the direction of the second one, right? So the chances you fall into like that lower tail, like that low or lower. And for two-sided, that's the probability that either one happens, right? Either your Z is bigger than or equal to this Z star, or less than or equal to that value. That's the chances that you are in that tail or that tail, in either of the two. Let me just say one thing before we move on, because we're going to, you know that your tables, your Z tables always go this way, right? So stuff like this and this are going to be a little bit problematic, right? Only a little bit. The probability that we're going to use this a lot, Z is, say, bigger than or equal to 2. You could use your complement rule, that's totally fine. Or this is the same thing as probability that Z is less than or equal to negative 2. Do you buy that? Okay, because that's like saying, okay, well, if this is 2, this area, and this is negative 2, those areas are equal, right? But you also could use your complement rule. That would not be wrong either. How about this second one? Like if this were 2 and this were negative 2, positive 2, what's the probability that, and this one should be, Z is bigger than or equal to 2, or this should have said negative Z star. Either you're above.
Wouldn't it be 0?
Well, or those are two mutually exclusive events, right? Yeah, so you'd add them together. Probability that Z is bigger than or equal to 2 plus all those probability rules again, right? If it was and, then you're totally right, it would be 0. But do you see how that's sort of, these two things are symmetric, right? So it's twice whatever you get for one of those two. So this is 2 times the probability that Z is less than or equal to negative 2. And we'll see specific examples where we deal with all these situations, so.
Are we going to deal with situations where it's like -3 and like +1?
No, it will always be symmetric.
Okay.
Yep, it's always one or the other. Yep. Okay. So let's practice using your Z table to find these values. So if your Z statistic is 2.10 and your HA is that the probability, your P, your proportion is not equal to 0.1. This is a two-sided test, right? Okay, so that's the probability that the Z is either bigger than or equal to 2.10 or Z is less than or equal to negative 2.10. Which we just said is probability Z bigger than or equal to 2.10 plus Z less than or equal to negative 2.10, or twice probability Z is less than or equal to negative 2.1. You can skip the middle step if you understand that the last step happens, where that comes from. So can you find this probability in your Z table? So look for negative 2.1. What do you get for that? The P values are the ones like inside the bulk of the table. So what do you get when you plug in, look at negative 2.1? 0.0179, yep. So that's 2 times 0.0179, which is 0.0358. Since these tables have 4 digits, just keep 4 digits in all your homework. Don't worry about my whole like arbitrary 3 rule, just do 4. So that's your p-value. Now, if your rejection level, which is a set different for different situations, but if it was 0.05, would you reject H naught? Yes. But this said that the level was set at 0.01. So if so what that means is your p-value must be less than 0.01 to reject H naught. Is that true in this case? No. So you fail to reject.
Are you sure it's 179 or 174?
I'm sure it's 179 because 174 is negative 2.11.
Okay, I see.
Does that make sense?
Yeah, I got it.
Okay. So fail to reject H naught. And that's because this confidence level is set kind of harsh. Okay. People will do that if you're testing lots of hypotheses, like for genetic testing or some kind of genetic stuff, for testing lots of different things. I've got a great XKCD comic I can bring to you about jelly beans and lots of hypothesis tests. Okay, it's funny. Okay, if your Z statistic is -2, your P is 0.6, and your HA is that probability is less than 0.6. So first of all, is it kind of important that the Z statistic is negative? Do you see what I'm saying here? That we're testing the proportion that our proportion is less than 0.6, which means we really want to see, well, what's the chances we fall sort of on the negative direction, right? Less than that mean. So what's the chances that Z is less than -2? What probability do you get for that?
0.0228.
0.0228. Is this small enough? Mm-mm. If our rejection level is 0.01, this is not small enough. And as a result, you fail to reject H0. Mm-hmm. Okay, how about the last one? I don't know if I have that on the next slide, but let's just assume I don't. Okay. Goodness gracious, that's got crazy Z statistic, right? We have Z is 4.25. And we have a H0 is that the proportion is equal to 0.25. I put an extra 0 in there, sorry. And HA is that P is greater than 0.25. Okay, so we're looking for what's the probability that our Z value is bigger than or equal to 4.25, which is the same thing as what?
Less than -4.25.
Mm-hmm. And 4.25 isn't in your table, is it? Like, I'm not being a meanie, it actually isn't there. Do you agree?
4.26.
4.26 is though, so that's probably close enough. Does that make sense? So what is that probability?
0.00001.
4 zeros?
Yeah.
Yeah. Okay, is that small enough?
Yes.
Yes. Woo. I'm gonna reject that H0. And I'm gonna say that HA is the new truth. Okay. So does how to use the table make sense? You use a lot of the negative side, because that's the side that goes the direction that you want. Okay. There's a couple conditions that you should check before you conduct the Z-test. The first thing is that your sample has to be a random sample, which can often be hard. People have to actually answer their phones and talk to you. If it's that kind of study, right? If it's something else, maybe they have to actually participate in your study. You can't only get poor college students to like test your drugs, which happens a lot with drug studies, right? Okay, and also the quantities N times P0 and N times 1 minus P0 should be at both be at least 10. So what these are the number of people in each category. Or things. So, and at least 10 means bigger than or equal to 10. So how big your sample size is depends a little bit on what that null value is, or how big it needs to be, that is. So for example, I look at this next one. For example, we have 20 students are selected from the list of sorority and fraternity members at a university to figure out if a majority of them favor a new alcohol policy. So if these are your hypotheses, is 20 enough? Does that make sense to sort of make sure that you're, so in that case, you need to check, what's your null value? The null value is 0.5. So check what is N times P0, 20 times 0.5 is 10, sure, okay. And n times 1 minus p naught is also 20 times 0.5, which is also 10. So are the samples big enough? Yes, but barely, right?
Yeah.
But what if that sample proportion changes? Is that going to work now? What's NP naught in this case?
20 times 20.
Which is 2. Wee-oo, wee-oo, wee-oo.
Too small.
That's a problem. That means you only expect 2 people in your little group to display this characteristic, which is just kind of rare, and you could get samples where they're either over or underrepresented pretty easily. Okay. So ready for some real data from some real life surveys? I grew up Catholic, so I find this one kind of fun. I was always very offended that I couldn't be a priest, even though I didn't actually want to be a priest. So, just the fact that I couldn't made me angry. So, you probably can see that knowing me a little bit. So, Time magazine reported in '94 that a survey of 507 randomly selected adult American Catholics, 59% answered yes to the question, do you favor allowing women to be priests? So, state the null and alternative hypotheses for deciding whether more than half of American Catholics in '94 favor that policy. Okay, so H naught, HA. So we'll do symbols and then words. So HA is that the proportion is more than 50%, right? So that's P is bigger than 0.5 or more than 50% of American Catholics support women being priests. Notice this was American Catholics, and that might not include like people in other places like Latin America, right, where Catholicism is big. What's HA gonna be? Less than, or you could just say equal to as well. Okay, it doesn't actually matter, but less than or equal to 0.05. So 50% or less support women being priests. Okay, awesome. What conditions are necessary to use the Z statistic? Well, you have to have that n times P naught and n times 1 minus P naught are both bigger than or equal to 10, right? What sample size do you have? Times our null value, which is, our null value is just 0.5. That's the breaking point. So half of 507 is 253.5. That's definitely met, right? The other one's also going to be the same thing, isn't it? So, yes, both n P naught and n times 1 minus P naught bigger than or equal to 10 by a lot.
And 10 is going to be the number we use for all of them.
10 is the number used for each of them. Yep. Which is definitely a bit arbitrary. So, but that probably is the point at which it just levels out good enough, basically, if you take any samples. Okay, find the test statistic. So we have this Z value is P hat minus P naught over the standard error of P naught. So first, let's find the standard error of P naught. So it's root P naught times 1 minus P naught over N. what do you plug in for P naught? Mm-hmm. And then for N goes, great. This comes out to be 0.000. Oh no, I was looking at the wrong problem. Sorry. That's not right. Just 1 0. White out. Just like outside. 022361 is what I got. There we go. Okay. So the Z score is going to be given by what goes in for P hat. What's the proportion you actually observed? 0.59 minus 0.5 divided by 0.022361, which comes out to be 4.024 is what I got. Does that make sense?
Yep.
Okay. So calculate the p-value for this test. So what's the probability that our z statistic would be bigger than or equal to 0.024? That's the same thing as the chances that z is less than or equal to negative 4.024. And that's not one that's on our table, right? But do you agree with this? Do you agree that this is less than 0.0001? Where did I get that one from? 3.72, right? 4.26 is too far away, right? So it's certainly less than the negative 3.72. If this is a test, that's all you could do and that's good enough. You can't get me an exact thing. If it's a homework, here's how you do it in Excel, okay? You type in equals, the command is norm dist, and then you put in your z score specifically, like whatever number you got for z. And on your homework that you turn in, I want you to find z values using Excel if your table doesn't give you the value. Does that make sense? Okay, or you can also just like Google what is the, blah, blah, blah p-value for this z. You probably will do that too. Okay, I'm sure there's free software. You end up with 0.000, I was getting my zeros from before, 29. Does that make sense? Yeah, it's less than 0.3001, right? But it's also bigger than the z score for negative 4.26, isn't it? Okay. So that's one way you could know if your z-score with Excel was plausible, right? Did it fall between two things that you think it should have fallen between, right? Okay. Anyhow, this is a probability. That is a really, really, really small number, right? Which means this is really, 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 really unlikely, yes? Okay. So, what do? Suppose we use level of significance 0.05. Do you reject H naught or fail to reject H naught?
Yeah.
You reject that H naught. Out with the men, in with women. Sorry, okay, sorry. That's totally how it goes. So, sorry, guys. Okay, so reject H naught. And accept HA. And I would like a conclusion in words as well, because I want to make sure you understand what that means in the context of your situation. Like, your grader's not going to check that so much because they've got a lot of papers to grade, but I actually read your quizzes. It takes a while. So, this would say more than 50%. You could also say a majority of American Catholics supported women in the priesthood and be specific that this is actually in 1994, it is very likely that the opinion has changed since then, right? Oh my God, that was like, what, 20 years ago? 22 years ago? Remember that year. Okay. Wow, okay. So, I think that in general, I'm a little bit biased, but I really, really prefer confidence intervals because in addition, like that just said, okay, well, it's more than 50%, but it doesn't tell you how much more than 50%. Does that make sense? Whereas a confidence interval gives you this like range of values where you can see, oh, how close is it to 50%? Like kind of close or like really a lot like bigger, right? So let's find a confidence interval for the proportion of American Catholics who favored allowing women to become priests. And we'll see, does this support the same conclusion as our hypothesis test, which it definitely will. So to find that confidence interval, you need the standard error of p hat, right? That formula was p hat plus or minus your multiplier times the standard error of p hat. And because our sample size is so big, and we're looking at a 95% confidence interval, what are we going to use for our multiplier?
2.
Yep. Your table, you'd have 506 degrees of freedom, which might give you like z equals 1.96. You can just use 2, it's okay. Okay, this formula, remember, is root p hat, 1 minus p hat over n. What is the p hat that we observed? 1 minus 0.59 over 507. That comes out to be 0.022. Okay, so your 95% confidence interval is 59%. Plus or minus 2 times, what is 0.022 as a percent?
2.2%.
So 59% plus or minus 4.4%. Or 54.6% to 63.4%. So, does this support the conclusion that a majority of Catholics favor the priesthood, or women being priests? We'll say from part E, and the answer is yes, it totally does, because this is your list of plausible values for that proportion, right? And they're all bigger than half. Yes? So all values fall above 0.5/50%, right? But it is a little bit close, isn't it? You see what I'm saying? Like that low end is kind of close to 50%-ish, right?
Yeah.
So do with that what you will. So suppose that a two-sided test for a proportion resulted in a p-value of 0.07. What that means in a picture is that you found the area of both of these little bitty tails, and together they added up to 0.07. Does that make sense? Okay. Using the usual alpha equals 0.05 criterion for hypothesis testing, would you conclude that the population proportion was different than the null? In other words, would you reject H naught or fail to reject H naught in this case? If it was a two-sided thing, right? Is the p-value you found less than 0.05? No, it's awfully close, right? Close doesn't count. You don't get to like adjust your p-value adjust your threshold because you don't like what happened. Well, you fail to reject. You pick that alpha, right? As in, like, this is not necessarily set in stone. You could just change your alpha to like 0.8, 0.08. And you say, okay, I now change my mind and I'm going to, reject H naught. But the point is, in this case, because it is a two-sided thing, and even though that P is close, you still fail to reject H naught. Suppose the test was a one-sided test instead. If it was a one-sided test instead, how would that change the p-value? It'd be half that, it'd be smaller. 0.07 divided by 2, which is 0.035, right? So now, what do?
Reject.
You reject H naught. So I think the moral of that story is that if you have a suspicion about the direction, maybe you should specify it. Does that make sense? Okay. All right, I like this example because I want to squash your idea that guessing on multiple choice tests is a way to get a good grade, because it just doesn't work that way. Studying is a good way to get good grades on exams. So we have a multiple choice test, and it has 50 questions with 4 choices each. And a teacher wants to test the hypothesis that a student is just guessing versus the hypothesis that the probability of correct answer would have been higher than if the student were guessing. So what is the chances that, the correct proportion of responses they have is just guessing or due to chance? Does that idea kind of make sense? So what do you think? Nothing going on would mean that the probability of success was just straight up, they have a 1 in how many chance to be right on a question? 1 in 4. So the probability, the proportion of successes is equal to, or we'll just say equal to 0.25, or less than or equal to.
Are we finding the parameter of the choice rate and the null and the alternative?
Oh, whoops. Sorry, skipped ahead. The parameter is the probability of a correct answer on each guess. Thanks. Or it is, how likely is it that, say, certain score is due to chance? This is a bit wishy-washy. So if nothing is going on, what's your chances of success?
0.25.
So that'd be P equals 0.25. Versus HA, the student actually studied, would mean that their proportion of success probably is
0.7.
bigger than 0.25. Does that make sense? Okay, and this is kind of binomial review because this is an experiment, right? How many trials were done? And what's the chance of success? How many questions did they try on? 50, so 50 trials. What is the probability of success on each trial? 0.25. So if a student chooses the correct answer on 25 of the 50 questions, what's the exact p-value for this hypothesis test? So what's the probability that they're going to get 25 questions right or more? Does that make sense? That's kind of like what this hypothesis test is doing. What's the chances that you're this extreme or more extreme? And I want you to use a homework question like this. I want you to use technology, but technology only goes the other direction. So what's the opposite of getting 25 or more right? 24 or less. Does that make sense?
Yeah.
So 1 minus px less than or equal to 24. And then you find this thing using technology, and here's how you do it in Excel. The command is binom dist. You put in your k, which is 24, your n, which is your number of trials, which is 50, the probability of success, and then a true or false saying, is it the exactly equal to or the less than one? True is the less than one. Comes out to be 0.999877. That's pretty. So in that case, what's going to happen to the thing we actually want to know? It's going to be very small, yeah. The probability that x is bigger than or equal to 25 is 1 minus that number. It's, yeah, what, 3 zeros, 1, 2, 2? Yeah. So if you're guessing, is it very likely that you're going to get a score of 25 or higher?
No.
No.
No, okay? So don't do that. Study for your tests. Multiple choice isn't better. So if a student, well, conclusion can be made about whether somebody who got 25 correct answers was guessing. Do you think that they were guessing on every single question? Yeah, so they were probably not guessing on every question. As the probability of getting 25 out of 50 or higher just by chance is only 0.000123, which is super small. So it's likely that they were definitely not guessing. But I thought it was good to kind of review the binomial thing a little.